Good afternoon and welcome to today's webinar, Ocean Transportation Reliability, Myths, Realities, and Impacts. My name is Tara Faulkner. I am the Director of Communications here at the Center for Transportation and Logistics. Throughout the presentation today, you will have the opportunity to type in and ask some questions. At the end of the presentation, we will be happy to address those. If you have any technical issues, please use the chat function. And for questions for our panelists, please use the Q&A function. I have the pleasure of introducing our speakers to you today. Dr. Chris Kaplis is the Executive Director for the Center for Transportation and Logistics. Prior to this, he served as Executive Director of our MIT Supply Chain Management Master's Program. He's also the founder of the MIT Freight Lab, which is a research initiative that focuses on the way freight transportation is designed, procured, and managed. Dr. Bashak Kalkanji is a postdoctoral associate here at the center. She received her PhD from Stanford University. So without further ado, I turn it over to Dr. Kaplis.
Thank you, Tara. Good afternoon, everyone. So I'm going to talk for a little bit, then introduce Bashak, who will take you through the first part of the talk, then I'll come on at the end. But I wanted to give a little bit of background on this whole research initiative. Our whole interest in this ocean transportation reliability really began back in the fall of 2010 when a partner of ours, a large global manufacturer, asked us, how reliable is our ocean shipping? He was a fairly senior executive at the company, and his concern was that he thought that they were managing more by anecdote than by actual analysis of the data. They heard the horror stories of having to airlift very heavy parts across the world when ocean reliability wasn't there. And he did want to see if that was true or if it was fiction, or really to get to the bottom of it. Now, this was a company that had a manufacturing strategy that specialized each plant, so they were shipping from everywhere to everywhere, as opposed to having a local manufacturing hitting the local market. So we looked at this, and we looked at their data, and over the course of the last couple of years, we've done a fair amount of work on this. We have a team that has worked on this at different areas over different times. Dr. Bruce Arntzen, myself, Dr. Kalkanji, and Lita Das, who is a PhD candidate. And so we've all done some work on this over the last 2.5 years. And the main activities fall into two buckets. The first is, after we did the analysis of that first company, we dove into many other companies, about a dozen. And these are mainly U.S.-centric companies, whether importing or exporting from the U.S., but it also included shipments to and from Europe, Latin America, and Pacific Rim. So it's global, more or less, but did have a U.S.-centric focus for the most part. And we looked at transactional data at the container level to find out when shipments moved, the reliability. We tried to get end-to-end data from the original origin to the final destination with all timestamps, entering a port, leaving that port, arriving at the destination port, leaving that destination port, and the land leg into the final destination. So we tried to get end-to-end data. In addition to the analysis that we've done, and we'll talk some more about that, we've also held a series of roundtables. We do these in the fall, and what we do for these, we try to invite 2 to 3 dozen representatives from shippers, carriers, forwarders, and other relevant entities, and we have an open dialogue for a day and a half. We generally apply Vegas rules to this, and then what is said at the roundtable stays at the roundtable. We found that helps cultivate better discussion. And out of this, it's helped us focus our research and kind of give some more flesh to the findings that we have from our analysis. So the key research questions, and these are the questions we're going to answer or try to talk about today, is one, how do the perceptions of ocean transportation reliability match the reality of ocean transportation reliability? That's what Dr. Kalkanji is going to talk about. And then I'll come back on and talk about the second one, is when should a shipper care about reliability and when should they not? And so it's more about building the business case for caring about reliability of the ocean transportation. So without any further ado, I'm going to turn it over to Bashak and let her take over and talk about the 6 myths of ocean reliability.
Thank you very much, Chris. This is Bashak Kalkanji, and I'm a postdoctoral associate at the center. So I'd like to first talk a bit about some of our surprising findings from this study, where we were expecting one fact, but we obtained another result from our interviews and our data analysis. The first 3 myths I'll talk about are related with a project that we did with a major US company which was unhappy with the reliability of their ocean carriers. So our main motivation in this study was to explore the ocean carrier relations to be able to find out where the problem is originating from. So we first interviewed key individuals in the organization, and we also analyzed the data on their ocean transportation. So the first observation was reliability meant different things to different people. To understand what reliability meant, we conducted a poll, and this poll revealed that the reliability concept actually had 2 facets in this company: the credibility and the schedule consistency. So what did credibility mean? So in this company, if the carrier was doing what it was supposed to do, so reserving the slots as agreed to, stopping at all the ports that's been agreed upon in advance, and also loading all the containers that it was committed, then the carrier was perceived to be credible and so reliable. The second dimension was the schedule consistency. So if the carrier was close to what it was saying in the coded schedule, and if the transit times are consistent, then the carrier was considered to be consistent with respect to the schedule, and again, reliable. But even the schedule consistency definition was not consistent. So this company was a global company with different operating regions in North America, Europe, South America, Asia Pacific, and Africa. And we actually found that different people at each region were using different definitions to capture the schedule consistency. So here in this slide, you can see 3 most cited definitions that they used. So some people were comparing the actual transit times to quoted transit time in the contract. They often also added some buffer time. So the measure was contract time plus 2 days, for example. The second one was comparing the actual transit time to the carrier's most recent performance, and again by possibly adding some buffer time. The third alternative was comparing the actual transit time to the published ship schedule. So for this company, there was some time between when the contract was agreed on and when it actually started to be executed. So the company was trying to keep track of the changes in the schedule and the string and vessel information of the carriers, and then using that information to keep track of the reliability of the carrier. The fourth one was actually a candidate that we came up with, which was looking into the tightness of the distribution of the transit time distribution. So if you really want to keep the carrier within a certain band of performance, you may calculate the percentage of times where he is plus to minus 2 days of the mode of the transit time, so where the most frequency occurs. But since the definition was not consistent, it's not really straightforward to formulate this as a key performance measure in the contract, so that it was not really built into the relationship between a carrier and a shipper. So since the carriers are providing transit time codes in the bidding process, we thought that they would be obligated to obey this code. And we've actually found that this was not true. We studied how the ocean carriers perform with respect to their delivery time estimates. So in the contract with the carrier, typically the carrier provides an estimate of the total transit duration. So what we did was comparing this estimate with the actual transit time duration. And as you can see from our analysis, here the x-axis represents the contracted transit time and y-axis represents what's actually going on in the data. So it's the mean actual transit time. And as you can see, in almost all of the lanes, the actual was above the contract. So the ocean carriers are typically taking longer than what they specify in the contract. We actually did more into the data to understand where the problem was occurring and where we see the most deviation from the contract, we looked into 3 different segments. So one was the origin port throughput, which is the total dwell time that the container spent at the origin port. And then we had the port-to-port segment, which is just the transit from the origin port to the destination port. And then the last segment was the destination port throughput, which is the dwell time of the container at the destination port. As you can see, the port-to-port transit time was quite accurate. So the actual and the contracted time was quite close to each other. But when it comes to the port throughput estimates, they were hugely different from the contract. So we see much more delays at both of the ports. Now, the companies may also look into the private data sources to understand how reliable a carrier is, and they make their planning accordingly. But these private data sources typically look into a port-to-port performance. In other words, it doesn't really take into account the port dwell times or the land component. However, our analysis actually showed that the port-to-port performance provides a partial view. To understand this, we divided the total transit into 5 legs. So we have the origin landside transit, so from the origin facility to the origin port. And then the second segment is the origin port dwell. The third part is the ocean transit. The fourth part is the destination port dwell. And then lastly, we have the destination landside transit, which is the transit time from the destination port to the final destination. Here, in the table, you can see the coefficient of variation in each segment, which is basically the measure of the variability of that segment with respect to the average time spent on that segment. As you can see, the port-to-port segment is the most stable leg with the lowest coefficient of variation. However, there is significant dwell time in the ports. Typically, it can take 3 to 4 days. And the landside legs have very high coefficient of variation and high variability. So this confirms that the port-to-port performance is not a good measure of end-to-end reliability, and the shippers must take into account the port delays and also the landside transit delays. A second reason why port-to-port is not a good measure is the carriers can actually differ dramatically on other segments of the route. Now, let me provide an example. We obtained data from a logistics provider who manages shipments for a number of different shippers. And we analyzed the container shipments of these different shippers across different ports and also managed by different carriers. And we actually found that the port dwell times of different carriers can differ dramatically. Here you can see the analysis for the Port of Los Angeles. So basically, this plot shows us that if all the other factors that affect the dwell time it's kept constant, then carrier S takes on average 60% longer than carrier C. So the efficiency of the carriers could be different significantly. And we also found that the port throughput times decrease when more terminals can be used by the carrier and when the carrier has a dedicated terminal. One of the most surprising things from this study was actually that the few shippers collect lead time reliability data. They don't typically use the data and feed it into their ERP systems automatically. And even if the ERP systems have some component of the data, it's only a single value for the lead time. It's not necessarily a range of values or even the standard deviation of the transit times. the shippers we spoke to also tended to analyze, make their analysis based on the worst rather than the average cases. And the business case for increasing the reliability was not clear. So the transportation managers typically had difficulty selling the importance of the transit reliability to the senior management. Now, one of the questions that's been asked to us over and over again was, how much is it worth for me to reduce my variability? We also heard from many companies about their initiatives to reduce days from their supply chains. So to understand how much reducing the supply chain days or reducing variability is worth, we performed a study with 2 retailers. So we collected shipment data from the 2 retailers, we looked into their transit times, and we also looked into their demand streams over the course of a year. And then we tried different scenarios. So we looked into the case where reducing the average transit time on each ocean lane by 3, 5, or 7 days, and also reducing the variability and the standard deviation of the transit time by 1 or 3 days. After we tried these scenarios, we compared the inventory levels to see how much is it worth to make these improvements. The most important finding was that reducing variability actually helps significantly. As you can see from the analysis in the table, reducing 3 days in standard deviation can be as valuable as reducing a week from your supply chain on average. So in other words, schedule consistency and punctuality are very, very important. We also found that reducing the transit time pays off more if the transit time of a lane is short and consistent. So if the transit times are very variable, it doesn't really make sense for you to try to invest to reduce supply chain days from your system. And we also found that reducing variability pays off more if the transit time of the lane is short but variable. So if the transit time is very high, then maybe it doesn't make sense to try to reduce the variability. And finally, the slow steaming issue is not well analyzed. So the impacts to the shippers are not fully analyzed up to now. In fact, Federal Maritime Commission inquired various carriers and shippers on the impact of slow steaming in 2011. The shippers and the carriers had very, very different perspectives. So National Retail Federation claimed that supply chain days are extended, but the cost savings by the carriers are not passed on to the shippers. However, the carriers such as Maersk, MSCU, and OOCL claim that although slow steaming increases the transit times, it also improves schedule reliability since the carriers now have more buffer between the port calls. As you can see, these are basically the claims of the shippers and the carriers, but we don't really have a lot of data behind this. So we wanted to collect some data on this issue as well. We reached out to a logistics provider, and they provided us with the port-to-port performance in different years for the same lanes. So as you can see here, there are some lanes where the transit time increased because of slow steaming, but the standard deviation is actually decreased after slow steaming. So the main conclusion is, although slow steaming may seem like it's hurting the shippers, it's also possible that it's reducing the variability. And the shippers must take a close look at what's really going on and how it's affecting the inventory levels. Now, with that, I'd like to hand it over to Chris.
All right. Thank you, Bashak. So I'd like to remind everyone, if they have any questions, please text those in. I don't want to have to cold call anyone and make you ask some questions. But I'd like for you to get some things so we can have some discussion. What I want to do is now talk about the business case. This question actually came about from our first roundtable in 2011 when a manufacturer who was mainly an exporter from the U.S. asked why they should really care. Why should they care about reliability? You know, how much is too much? Should they pay an extra dollar to go from 90% to 95%? You know, why should we do this? And so we decided to look at this. And over the course of the last year, we've dove into this in a couple different ways. First, the problem itself is a little tricky. Ocean transit time, as we'll talk more, is it's a varied dimension. There's three ways we can characterize it. One is, the most common way is look at a central tendency. This is the average, or we could do the median, the expected value, the mode, whatever, that tells me generally what is the most expected, or the central tendency of that distribution. And most people are pretty good with that. But we also need to look at the dispersion, and that's how the distribution, how the different observations vary from that average or that median. Are they all centralized? Are they symmetric? Are they widely dispersed? Are they close together? And then we have to look at the shape. And the big thing here is whether it's symmetric. Like with any transportation or transit distribution, the concern is, do I have a heavy right tail? Do I have more longer, slower shipments than I do have really fast ones? Generally, the law of physics keeps you from having too fast. And so usually in transportation distributions, you have a long right tail. But these are the things we have to think about. And then the idea of the central tendency or the average, that's fairly well understood. Most people have a good understanding, and in fact, when we talk to shippers, they can usually say for each lane they have, we know what the average transit time is, and that's one they plan to, and that's a lot of what Bashak was talking about. But the other thing that we had to dive into was, to make the business case, we also have to get somehow into the value of the goods being transported. And the way we did this, and I'll talk more about this in a few minutes, is getting to the trade-off of the shortage or holding cost, the overage and the underage costs, what the value is. If you have a very high, if you expect to never stock out, and it's a very high penalty for you to stock out, then you have a very high ratio here, what we call the critical ratio, and I'll explain that more in a second. But if you're shipping stuff that, you know, if it gets delayed by a couple days, a couple weeks, it's no big deal, then you'll have a very low critical ratio. And so we use that as a proxy to get a sense of how much the products are valued by the shipper, how important it is to get there on time. So when we looked at this and we talked to our partners and went out to the industry and wanted to find the current state of the practice. So there's really two main approaches. There's three ways you can go, and two are more common. The most common approach is to ignore any variability. It's just to take the average, put that in your ERP system, and on that transit time, on that trade lane, it takes 31 days, 32 days, and that's your planning number, and that's the only number that sits in your system and is used as the trigger to determine your safety stock and your cycle stock. By far, this was the most common approach we've seen, talking to the different software vendors as well as shippers. A second approach that can be used is a little more sophisticated, and we call this Policy 2, and the ignore it approach we call Policy 1, is to incorporate the variability. And what you do here is you include the variability of the distribution as well as the mean, and you consider it by determining a joint demand under uncertain transit time. So you know your demand is variable, and you want to tie that in to the variability of the distribution itself. And there's a classic way to do this, the Hadley-Witten equation. I'll explain it and actually show it to you in a second. But it's a way to get the convoluted distribution of two random numbers. So what the approach does is they apply this then to a normal distribution to set your safety stock. Now the third approach, which we haven't seen anyone use in practice, is actually an optimal approach. And this is much more complicated to create. You have to actually convolute the two distributions, the distribution of demand and the distribution of that transit time. And so we'll talk how we did this in certain cases to compare the different policies, but we know of no one who does this in practice because it takes too much time. You have to use the actual distribution, and so it's more of a theoretical approach at this point. But what we wanted to do is to see how these different policies react, and when does it make sense to use Policy 1, just to use the mean, and when does it make sense to actually incorporate variability. Because the lesson is, whenever you include variability into your consideration, you're going to increase the amount of safety stock, just flat out, because what it's doing, it's saying your variability is bigger, so therefore you need more inventory to cover for it. So whenever you move from policy 1 to policy 2, you are increasing your inventory footprint. The question is, when does that make sense and when does it not? So diving into this policy 2 a little bit, I want to explain what it is, and since this is MIT, I have to show an equation of some sort. This is the Hadley-Witten equation, and just really quick, all that it's doing, it's taking these two random variables, the L, which is the lead time, your transit time, and the D, which is your average demand of your product over each of those time units, and it's finding both the expected or the average value, and then it's finding that sigma, which is a standard deviation, and the DOLT is demand over lead time. So by using this method, what you're doing is actually finding the random sum of random numbers. It's a very well-known equation. It's in every inventory book. And then the idea is, once I know this new distribution that's convoluted of the transit time and the demand distributions, I can apply this new mean and this new standard deviation, apply to a normal distribution, and find my safety stock. So it works very well when you have a nice normal distribution. However, there are some cases where it doesn't quite work as planned. So let me give you a very quick case, and this is actually from a paper by Eppen and Martin in 1988, but it really illustrates where the weakness of this approach can come in. So I'm going to use this Hadley-Witten equation in two cases. Case 1, the blue case, is where the lead time is 4 weeks and there's absolutely no variability. Everything comes in 4 weeks with no randomness. The second case, or the green case, where lead time is split. It comes half the time in 2 weeks and half the time in 4 weeks. So in the blue case, the worst case scenario is 4 weeks, but it's always 4 weeks. In the second case, the worst time still is just 4 weeks, but half the times it comes twice as fast. So normal intuition would say, you know what, I should have less inventory required for the blue. I'm sorry, for the green. So because I'm faster, right? And so I shouldn't need as much. But if you go through the calculations, and all I do here is apply the calculations that were on the previous page to find the expected demand, and then I'm using this K, or safety factor, and then I multiply that by the standard deviation, and in the blue case, I get about 433 units is what's required, and this is the stock plus the safety stock. Now, if I do the same thing for the green and apply that Hadley-Witten equation, since I have a variable transit time, then it comes out that my expected demand, or what I need to stock for, is actually higher. It's 467 units. And so you look at this and it just doesn't seem to make sense. Why is something that has half the transit times are faster, why does that mean I have to have more inventory using this equation? And so that's the puzzle here, and there's been a lot of analysis on this, and it really comes down to what you're assuming the distribution is looking at. Remember, we said that the Hadley-Witten is typically applied to a normal distribution because that's what everyone does. It's a nice normal distribution. In this case that I just showed, case 2, it's not a normal distribution. In fact, it's a bimodal distribution, a distribution with two modes or two peaks in it. And that's really the underlying problem of when this policy falls apart, whenever I don't have a normal distribution. So at one of our roundtables this past year, we asked all our members that were there, what diagram best characterizes your typical ocean transit time distribution? And so we gave them these options, and you can see at the bottom, options 1, 2, and 3 are written out visually. 1 is a normal curve. 2 is what's known as a log normal curve with that very long right tail, a heavy or fat right tail. And 3 is what's known as a bimodal distribution, where I have two modes or two humps, one smaller than the other one. And then I asked them for something else, or if you've never thought about it. And so here's where the response is. Almost 2/3 had non-normal distributions. Log normal was the most common, which makes sense because you can only go so fast on a lane, but you tend to have some shipments that just take forever, that get held up for whatever reason. So it's pretty common to have a long right tail in your transportation distribution. But we were surprised at the number of bimodal. Almost 20% said they had mainly bimodal distribution. So this is something that made us dive a little deeper, and we looked at the data from many different shippers just to see if this wasn't just a perception problem with the executives, what the data actually said. And as we looked through, we found many cases, and it depended on the on the shipper, whether it was 10% of the lanes or 20%. It really varied. But these are some examples of 4 different lanes from different shippers, and they show different distributions of transit time. The top left one is, you can see it's bimodal, with the later time having the smaller hump. The next one on the top right is just the opposite. It is bimodal, but there's you have fewer faster shipments. And the bottom left is another bimodal, and the bottom right is more of a log normalish looking one with a longer right tail, where you can see the mode is right around 13 days, but it stretches out to 20 days on the long end. So what we see from the data then is that there is a lot of non-normal distributions out there. And so we wanted to look at that a little more. We also asked our survey, our roundtable attendees, what their consistency is for the door-to-door ocean transit time. Bashak has been talking about the coefficient of variation. That's what we asked them as well, which is just a standard deviation over the mean. And so we asked them, and we gave them a little definition, because this isn't a common term that is used by transportation guys, but just try to get an idea of what their variability looks like. And we gave them the example of a 30-day shipment. If it was plus or minus 6 days, then that will have a coefficient of variation of 0.2. And so we asked them, and this is what it looked like. What's interesting, 28%, a little more than a quarter, said they had a coefficient of variation greater than 0.6. And those are the ones in the 3 left columns, the 12 and the 16%. And what that would mean for a 30-day transit time is that it would have a standard deviation of 18 days. So it would be plus or minus 18 days. That's tremendous. When we actually looked in the data, we found the actual data was smaller, and the CV was usually less than 10% or 0.1. But this shows the perception. And there's a lot of perception that I have much more variability than is actually there. But it's something that brought out, and this will come to be tied together in just a second. But while we were asking them this, we also asked them about the value of their product. And the way we did that is we asked them to decide what the trade-off between holding and shortage costs are. And we gave them 10 options. And the idea was that they would look at what is the cost of having X days of inventory that it's equal to Y days in delay. And so the ratios here, 1-to-1, that's X to Y. And so the idea is that these translate into critical ratios, where the critical ratio is just a measure of the service level, and it's the balance between the overage and the underage costs. So if you think it's 20-to-1, 20 days of inventory is equal to 1 day of shipment delay, then what you're doing is you're really saying that it's a 95% critical ratio, a 1-to-20. And so we're giving them actually, we're critical ratios from 50, where I'm equally, I don't care whether I have an extra day of a delay or an extra day of inventory, I'm indifferent, all the way up to very high levels. So if you have very expensive products and you don't want to stock out, you're going to have a very high critical ratio, closer to 1. If you're really indifferent, you're going to be lower and down near the 0.5. And so we asked these shippers where they fell, and this is what the distribution looked like. So about 30% of just under a third said their critical ratio was greater than 90%. And those are the 8-to-1, 9-to-1, and 10-to-1s. No one said 20-to-1 here as a suggestion. But clearly a third said their critical ratio was greater than 90%. You can look at this as their service level is greater than 90%. But then there was about a quarter that had the critical ratio less than 80%. And those are the people with a ratio of 4-to-1 and lower. So obviously our distribution, our participants were very split. Some people said, 90% and higher. Other people said 80% and lower. And the majority, the middle, was right there between the 80 and 90%, right in the 80s. But this showed that we had a variety of different people there, both importers, exporters, of high-value items, of low-value items. And this is a good way to kind of capture that. So we're going to use this data in a second, and I'm going to show you how we fit this into the analysis. But what we wanted to do now, remember, getting back to the business case. When does it make sense to care about reliability, and when should I use a different policy? So what we're trying to figure out is comparing these different policies, Policy 1 and Policy 2, with the optimal inventory strategy. And so, like we said, the comparison will depend on what that distribution of the time looks like, what the trade-off for that individual company is between underage and overage cost, that critical ratio we just talked about, and also what the demand distribution looks like. For this analysis, we made a couple of assumptions. One, we assumed that the demand was normally distributed. We made a very simple assumption here. It's pretty common for the demand of the product. We used a range of critical ratios. We went from 0.5 up to 1 just because we didn't really see anyone have a critical ratio below that. That means you'd rather stock out than hold any inventory. That really doesn't happen too much in these industries. And then we compared them to log normal transit times. Now remember, when we surveyed our roundtable participants, that was the most common distribution. That's that heavy right tail that we show here in the right corner. So what did we get from this? We're running the scenarios, and we did it for all these different critical ratios, for different transit times, and for different coefficients of variation of transit time, and we wanted to see when it made sense to use policy 1, and when did it make sense to use policy 2. And this is what we ended up with. Let me explain this chart. The horizontal axis is the critical ratio, going from 0.5 to 1, and on the left, the vertical axis, is the coefficient of variation that we've been talking about, which again is the standard deviation divided by the median. So if I have something in the bottom left quadrant, that means it's a very low value product, very low critical ratio, and it's on a lane with very low coefficient of variation, a very stable lane. If I go to the top right corner, that means I have a very high critical ratio, a product that I never want to stock out, and it's on an exceptionally variable lane. I have a high coefficient of variation. So that's what the chart looks like. And the idea is, this line that's here was generated by the analysis where we did different comparisons, and that's kind of the frontier for when it makes sense to use policy 2 versus policy 1. Remember, policy 1 is where I just ignore any variability and I just use the average value. Policy 2 is when I actually use the Hadley-Witten and I compare it and apply it even within a normal distribution, just applying it normally, and but I take that variability into consideration. And so you can see there's definitely a frontier here. Now, why would it ever make sense to use policy 1? Well, it makes sense when your critical ratio is very low, because then you don't want to have that extra inventory. I mean, you have all this extra inventory, but it doesn't make sense for your product. As that critical ratio gets higher, you see that more of the space falls into the policy 2 bucket. And the same thing with the coefficient of variation. Even if I have a high value item, if my variation, my coefficient of variation on the vertical axis is very low, then it doesn't make sense to have as much extra inventory because I don't have that, I'm not on a variable lane. Where it falls in is when I have a higher critical ratio, generally better than 0.7, 0.75, and then I'm on somewhat variable lane, and then it falls into that right quadrant, the top right quadrant of this chart. So what we did is we plotted, just for fun, the participants in the roundtable survey to see where they fell. And you can see they fell into these 3 buckets. The majority fell into that 80% bucket. That's it, where 80% of the participants fell. And they had a critical ratio between 0.8 and 0.95, and they tended to be on lanes that were at least 0.35 coefficient of variation for their variability. So the vast majority fell in there. But there was about 20% that fell out. Most of these were had a very low coefficient, critical ratio rather, which means low value products. Didn't matter if they stocked out that much. But some also were on very stable lanes. And so, and remember, this is just what their perceptions were, but we just wanted to see how they plotted. But it was interesting that the ones that are outside and that are in that policy 1 region tend to be exporters. And that makes sense because a lot of the export that we have from this country is of low-value items, whether it's waste product, different things that are not as critical as importers who might be bringing high-end electronics and other things like that. So we thought this was interesting. This is something we want to continue to look at to find out when the different policies make sense. Now, as I said, we did this for the assumed log normal distribution. But then we also did it with that bimodal distribution. Now, remember we said we saw a lot of this in actual data, and the participants actually said that they saw this about 20% of the time, or at least 20% of the shippers said that they saw this as well. And, so we started asking, why would you ever have bimodal transit times? And there's 4 possible reasons, and there are probably many others. The most common is getting bumping of freight at the origin port that makes it go to the next string, usually a week later. So a lot of times we see distributions where there's a second smaller mode or hump 7 days off of the mean of the first hump. And that just means it got bumped and it's on the next week's shipment. When we have a weekend delays in offloading freight, sometimes you get like a 3-day bump where it moves a little bit apart. If you have multiple carriers handling a single trade lane, they might have different transit times. The strings might be working in separate directions. One comes in and heads from the north to the south, the other comes the other way and goes south to north. So you might have one with a 24-day transit time and someone on the same trade lane is giving you a 30-day. So in that case, the bimodal is really 2 different carriers' distributions. But for your inventory purposes, if they're carrying the same freight from the same supplier, it really doesn't matter. It still shows up as a bimodal distribution. And then also slow steaming. If they change between slow steaming and normal steaming, you'll also see this as well. We don't see that as much, or we haven't seen that. I'd say the bumping and the multiple carriers explain the vast majority. But in any case, it's a real problem. And so this does happen. So we wanted to run the same scenarios, and we're still in the middle of doing this. We want to compare if you had a bimodal distribution lane and you had these 2 policies, when should you use one or the other? And again, we had the range of critical ratios. We assumed the demand was normally distributed. And what we did for the bimodal transit times, we actually did it for different levels of bimodalness. And what we mean there is the distance between the modes. So if it was 0, that means they're right on top of each other. And if it's like 12, that means that the humps are 12 days apart. And so what we do is vary that, and as that gets longer, it becomes a much more of a bimodal distribution. So it's kind of getting to the level or the degree of bimodalness. Now this is work that is ongoing. Our PhD candidate, Lita Das, is working on this along with Bashak. But some of the initial results kind of echo what we saw for the log normal. And for this, it's even more so. Where policy 2, that one where we use the Hadley-Witten equation to include variability into the inventory calculations, is always better whenever your critical ratio is greater than 0.5, which means it dominates. And so there's no zone where it makes sense for to use policy 1 to ignore the variability when you think you have a bimodal distribution. However, we did find that the policy 2 deteriorates as a proportion of the optimal solution as the distance between the modes increases. So the more it becomes bimodal, then the worse. Policy 2 is still better than policy 1, but it's not as good as optimal. There's some interesting things going on. We're just starting to look at this a little more, and we'll probably have more results to show later in the year, certainly at our next roundtable in the fall. But so what I wanted to leave on, let me just go back to this slide. This is what I really think was interesting, because this kind of helps us make the business case. And this helps you decide when you should even worry about and start thinking about when you want to consider changing your ERP or being able to include or modify your inventory levels, is to see where you fall. And so I'd love to find out more from different companies where you fall in this, and this is something we'll continue to talk about over the course of the year and certainly at our roundtable next year. So on that, let me just wrap up by saying some of the key takeaways that we see from this project so far. First, there is still a lot of management by anecdote versus management by analysis. I don't know, the only way we can try and do better here is to do more analysis and show those results, but there still seems to be a big separation between what the executives think and what the people on the ground actually know. Next is this perverse effect of slow steaming. It's really interesting in that yes, it does increase the average lead time, which you would think increases the safety stock and the cycle stock, but by reducing the variability, it actually does reduce the amount of safety stock that you need. So it's actually perverse in that it can actually lower. And as we've talked to more shippers, no one has really said, we haven't found anyone who's really said, oh my gosh, my inventory levels went up X% and it's horrible. Mainly people are just mad because the carriers are saving money and they're not passing it on. We haven't really seen it as an increase in inventory. I'd love to talk to anyone who's seen that and to dive in deeper, but we have yet found evidence of actually increased inventory levels. The third is that we found that different legs have different levels of reliability. Bashak was talking about this, and usually the one that people measure the most, the port-to-port, is probably the least important because it has the most stability. It's that land side, those land side legs, mainly on the origin side, land side, that you don't control, that causes most of the long-term problems. The other thing is that ocean transit times tend to be strange with this bimodal or this long right tail, and we kind of talked about that. That makes the inventory calculations a little complicated. And then finally, the business case for reducing reliability is not always clear, and that's what I spent the last 20, 30 minutes talking about. But what it seems to depend on is the play between the variability of the transit time and your overage-underage cost trade-off, or that critical ratio. And that's what I think would be very helpful for companies to start thinking about this and maybe think about which trade lanes fall into this category and which ones don't. Because like with anything, segmentation matters here. And I think having one policy for every lane that you have in your company probably doesn't make sense. And that what you need really is to segment and see which lanes make sense and use this critical ratio coefficient of variation phase policy 1, policy 2 chart we showed, maybe guide you in where you should pay your attention. And with that, I'd like to turn it over back to Tara and see if there's any questions.
Great. So we do have some questions that we'll address now. The first question is, how did you calculate the effective standard deviation versus the average time on inventory holding, and was it based on cost?
Okay, so it's for the last part of the presentation. So we basically saw a particular trend. So we basically tried out different levels of standard deviation and mean for the log normal distribution and also the critical ratio. And we calculated the level of inventory and cost for each of these different levels of standard deviation, mean, and the critical ratio. And then we saw basically trends. So we basically saw that the ratio of the standard deviation to the mean for the transit time distribution and the critical ratio was affecting how the cost was affected. So,
great. Okay. The next question is, your research seems to suggest that carriers should introduce more shuttle or point-to-point service with mega vessels. Is that the case?
So the question is, does it make sense to have mega vessels? That depends, because that's a really good research question, because I haven't seen too much about batch queuing. And so the idea of these mega ships come in, it takes longer to unload them, obviously. And so what it does, it pushes more a bottleneck. And so yes, it lowers the cost per unit per container on the water, but it increases the cost per container as it moves through the ports. And that's what happens when you have something with the Maersk coming in with so many TEUs at one port. It can slow things down. If it's truly point-to-point, though, I think the question is kind of confusing. If you're really doing point-to-point shipments, you probably won't be able to justify one of the large mega carriers, because they're made up to really do more distributions. So you'd see them go to multiple ports, because there isn't that much demand between one origin and one destination for a very large one. What I do see happening, I don't know how reliability would fit into this, is where you come into logistics clusters, where you might have something come in through the Panama Canal, stop there, and then the logistics cluster will break the bulk and then distribute it out on smaller ships going north and south, down to Brazil or north up to the U.S. So I see more distribution of containers out, but I don't see too much for the mega carriers affecting the reliability. But Bashak, do you have an opinion?
Okay. The next question, as the gap grows bigger, the assumption is you can stop thinking of it as bimodal and more like two modes in the same relationship, like a normal distribution. Would you say that's correct?
So the way that we create for these tests are a bimodal distribution. We started with two normal distributions that they were right on top of each other. And then what we do is we move one of the distributions further and further to the right. So as those get further apart, it becomes less normal. As they get closer together, they become normal. So I didn't quite understand. As we move them further apart, they become less normal. And yeah, they're like two separate distributions, but we're treating it as one, because that's what we saw in the data.
And also the shippers cannot know which distribution will be realized when the shipment takes place. So it doesn't really matter that they are two separate normal distributions. It's essentially what the shipper is observing.
Right.
Great. Thank you. The next question, are shippers investing in technology, third parties, and or in-house HR to develop an optimal approach? that you know?
None that I know. So if you notice, the Hadley-Witten equation has been around since 1963, and the approach of random sum of random numbers has been around for centuries. Applying it to logistics has been around for at least 50 years. So I don't, and there's not a real rush to put this in. And I think a lot of it is because we don't know what the value is. People use that equation for other levels of strategic planning. And so there are companies out there that do inventory optimization that utilize this, mainly in conjunction with looking at multi-echelon inventory. But for ocean, I haven't seen any companies that do this, and we polled a fair number of companies and shippers and found no one who does that. If they do it, it's done strategically as a study once or twice. It's not embedded within the operating system. But it could be. It'd be an interesting project. I'd love to talk to anyone about it.
The next question, what can we practically do if an ERP does not allow addition of variability into LT data values?
Then I think what you can do is, again, it's a segmentation. So I think the first step is, first step 0 is collecting data. We're always shocked at the number of shippers who actually don't have their data, don't look at this data. So step 1, get the data and identify those lanes that you see as being fairly variable in terms of coefficient of variation, and then also that are moving more the higher value goods. And you can do a rough proxy with that critical ratio. So identify the lanes at risk. And then you want to try to identify and work with the carriers to reduce the coefficient of variation. But if you find that you really can't, then you want to identify those, and what you could do is set the inventory levels, calculate what they should be, assuming that optimal, and then set that, and what you're doing is you're padding. And so you pad on to your safety stock. And so instead of 30 days, whatever they have for inventory, you might go to 35. And so what you're doing is you're identifying the lanes where it makes sense to pad your inventory, and you're doing that kind of manually. But you can use a study to optimally determine what it should be. That's kind of a second best for that. Okay.
Next question, have you compared how throughput times varied at different ports?
Actually, we haven't done that yet, but it's something that we are interested in, and we collected some data. Unfortunately, for the shippers, it may be more difficult because they have different carriers transferring the goods. So, but we have some logistics providers data that can allow us to do this analysis. It's something that we are working on.
The next question, which leg of the shipment has the most variability?
It's typically the land side component that had the highest delays and highest variability. So again, going back to the coefficient of variation analysis I talked about at the beginning, it's usually the origin side delays. The origin side land has the highest variability compared to the mean.
And this seems like a perfect way to end. How can I get involved in the research?
Great question. So the best thing to do is contact either myself or Bashak. Our emails are shown on the screen. We'd love to get more data, and we're looking at this. We'd love to see different shippers. We'd love to get more data from around the world. Like I said, most of our analysis so far has been U.S.-centric, but we'd love to see how this holds and how it looks in different parts of the world. Second thing is, if you're interested, we're going to hold another roundtable in the fall, and if you're interested, let me know, and we'll see if there's room to invite. We try to keep it as very small, like I said, less than 3 dozen people, because we like to have the conversation very fluid. So the best way to get involved is to send us your data and give us a ring.
Great. Okay, so just wanted to let everyone know about a few more things coming up here at CTL. On April 18th, as you can see, we have a roundtable for our partners. So those of you who are with our partner companies, we would love to have you register for that, and that is the URL. You can also find more information on our website. And we also have our executive education course coming up the 11th through the 14th of June. And there's more information on our website. And I mentioned our partners. The Supply Chain Exchange is the name of our partnership program. And if any of you are interested more in finding out more about how to join the center, we would love to hear from you. And you can contact Bob Vaz, that is his email. And, of course, there's our website. If you have any further questions, do let us know. We look forward to seeing you or hearing from you at our next event. And thanks again for being with us today.